Assalamu alaikum, students. This is me, Khawaja Yasin. Welcome to another lecture of Slate with me. Let's study chemistry. When we talk about AS chemistry, as I mentioned in the previous video, that the topic of chemical bonding is there in the exam. It's a long chapter. It has intermolecular forces, it has bonding, it has hybridization, it has shapes of molecules, it has bond length, bond energy, and it has various questions and reasoning based questions from the intermolecular forces. But in today's video, we're going to talk about orbital overlap and hybridization. It's a very basic concept, but sometimes it confuses the students. So let's first talk about the orbital overlap. We have discussed it in the first video, the video of the first chapter, that how the s and the p orbitals have shapes. S orbital, a spherical shape. P orbital has a dumbbell shape. So know that these orbitals are, especially the orbitals of the outermost shell, they are going to bond with the outermost orbital of the other shell, other atoms. So outermost orbital of one atom is going to react with, bond with the outermost orbital of the other one. So that is how the bonding takes place. And the orbitals overlap. Just like that, overlap. In covalent bonding, the Venn diagram was there. So let's first talk about the head-to-head overlap. The head-to-head overlap is when the two orbitals join head-to-head, head by head. The head-on joining. So, the first type of head-to-head is an SS overlap. So for that, know that the outermost shells of both of them, both the atoms, the outermost orbitals of both the atoms should be S. So you see how these two S spherical orbitals are going to merge this way and ultimately form a shape like this, an ovular shape. Where we are going to put dots here that we're going to discuss at the end. Likewise, the other one is S-P overlap, whereas one is S orbital and the other is P. Since S is a sphere, any overlap of S will be a head overlap because every side of a sphere is the same. So see the S orbital and the P orbital, the dumbbell shaped P orbital, that's how they do the overlap. And ultimately we get an orbital of this shape. Just because these two have merged. Now I'm going to again put a few dots here. Lastly, the PP head-to-head overlap. PP can overlap head-to-head. These are the p orbitals, but these are the sides. So when they overlap this way, that's a head-to-head overlap. And ultimately the shape becomes like this. So that is a PP head-to-head overlap. Let me make the dots again. So what do we know about these three overlaps? SS, SP, and PP. They make single bonds. And hence, sigma bonds. So whenever this is involved, this will be a sigma bond. So all single bonds undergo head-to-head overlap. All single bonds. For instance, let's look at these examples. We have a hydrogen overlapping with another hydrogen. They will make such a molecule, such an orbital overlap, and that would be the shape. If we have one hydrogen and one fluoride, let's make fluorine. The outermost orbital of fluorine is p. So this will be, the outermost shall be p. So this would be p and an s overlapping. So that's what happens. And when we make a fluorine molecules, F2F, that's what happens in this one. So F2F will be an overlap. A P overlap, it's a head-to-head overlap. So these will be single bonds. We know it's HH, HF, and FF. But I made those dots. These dots are very important for the concepts. These bigger dots and then the smaller dots. Why? What do we know about that? That the density of electrons lie between the line joining the two nuclei. So in this case, as you see, these are the two nuclei and the density of electron lies in between. These are the two nuclei and the density lies in between. These are the two nuclei and the density lies in between. That is for head-to-head overlap, single bonds, sigma bonds. The other example is a sideways overlap. That is again P2P, this time sideways. This will overlap with the other one. And ultimately we get such a shape. So two p orbitals sideways overlapping, and ultimately we get cloud of electron here and a cloud of electron here. So that is for PP sideways overlap. So students, in this one, whenever a PP sideways overlap is happening, this is for double or triple bond. And we call it a pi bond. Either this or this. It's a pi bond. PP sideways. And as I said, it's for double and triple bonds. But know one thing. Let's say we have a carbon-carbon double bond. We will be studying that right now after this topic. So we have two bonds. Know that the first bond is a PP sigma bond and the second bond is the PP pi bond. The first bond will always be a sigma bond. The second will be pi. The third will be pi. We will be dealing with them. So that's what it is about. And where is the density of electron? Density of electron above and below the line joining the two electrons. This is the line above and below. So that is what we know about the shapes of orbitals. From this very concept, let's start hybridization. By hybridization, we mean mixing of orbitals. Just like a hybrid car, it can run on fuel, it can run on battery. It's a hybrid. It has the property of two. That is what the hybridization of orbitals will be about. Normally, hybridization is of carbon and nitrogen, but nitrogen is not in your syllabus. We will only be talking about the hybridization of carbon. So, for that, we need to understand the electronic configuration of carbon. Remember, only the outermost electrons and orbitals matter. This is the ground state. Sorry, that's a wrong figure. This is the ground state. But when we excite it, we know that the electron will go from here to here. So carbon 6 will form so we have 1s, px, py, and pz, 3p orbitals. That is what we know about carbon. Now what happens? Let's separate the orbitals. We have 1s, with 1 electron. And we have 3 p's. P, P, P. If we make the shapes, this is S, this is P, this is another P, and this is another P. So that is what we know, that we have that in a carbon atom in excited state. So from here on, we will study 3 types of hybridizations. The first one is sp3 hybridization. sp3. So what do we know? We know that s orbital is a lower energy orbital and p is a high energy orbital. But sp3, by sp3 we mean 1s and 3p orbitals will mix to make 4 sp3 orbitals. 1, 3 and 4 are the quantity. 1s and 3p. They will mix up and make 4 new orbitals of different shape. 1, 2, 3, 4. And each one of them will be called sp3, 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 sp3. So if we have these orbitals, these 4 will mix up and will ultimately make 4 of these. So 1s, p plus p plus p will make an sp3, another sp3, another sp3, another sp3. So we know that the energy of S is lower, P is higher. But the energy of 4 sp3s will fall in between. So, in between the energy. So now we've got 4 sp3 orbitals. They're all equal now. They're all equal in energy. Otherwise, carbon had one lower s orbital, 3 higher p orbitals. But this time the energy becomes equal. So we have studied that in the shapes of molecules. That we have 4 bonds and no lone pair. So what shall be the shape? Carbon will make this, 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 and this. This shape is a tetrahedral shape. And we ignore these smaller lobes because that is going to complicate the structure. So that is what we make a tetrahedral geometry. And if I make methane out of it, this, now that we have 4 hydrogens with it. So what type of question can you get? How many and what overlaps are happening? This is an s orbital. This was an sp3. So what are the overlaps? We are having 4 sp3s overlaps. And how many bonds? 4 sigma bonds. That's one example. Likewise, if we make ethane, let's make the same carbon. 1, 2, 3, 4. This would be C2H6. Now, there is a carbon-carbon bond, we know that. Then, this is sp3, this was sp3, this was sp3, this was sp3. They were all sp3. But now let's add hydrogens. So what are the overlaps? So students, let's count them again. 1, 1, 2, 3, 4, 5, 6. So we have 6 sp3s overlaps. But what about this one? We have both sp3. So we have one sp3 overlap. And the angle in both the cases will be 109.5. And whenever carbon is making single bonds, that will always be sp3 hybridized. And the shape will always be tetrahedral. That is sp3 hybridization. Now let's talk about sp2. Students, in the sp2 hybridization, as the name says, We have one S. Now we are left with one S and 3p, 2p have mixed. And ultimately we get three hybridized orbitals. 1s plus 2p. So these will be sp2, sp2, sp2. What about the third p? Third p was not involved in hybridization. So since this s and these p reacted, we will still have, now in an sp2 hybridized carbon, we will have three sp2 orbitals and one p orbital. And remember, p is higher in energy. This is what we have. Now carbon has three orbitals, three bonds. What was the shape? In the last video you can see that whenever carbon is making or any element is making three bonds and no lone pair, we would get a trigonal planar shape. That's what we get. And the angle is 120 degree. Now let's talk about another carbon, sp2 hybridized, overlapping with this one. That's perfect. We are talking about ethene. So we have just two lobes left for hydrogen in each way, each carbon. That's perfect. So we have carbon has filled 1, 2, 3, three of its valencies. 1, 2, 3. What will be about the fourth one? Remember, there was one p orbital. Then we draw this p orbital in its original shape because this was not hybridized. This will come in its original shape. These will go sideways overlap. And therefore ultimately we will get a cloud just like we did it here, two clouds. So students, it's a pi sideways, it's a pi bond, it's a pp sideways overlap. So let's count the number of overlaps. 1, 2, 3, 4. We have 4 sp2 s overlaps. We have 1 sp2 overlap. And we have 1 pp overlap as well. This was sideways. And as I said, the pp overlap accounts for the second bond in a double bond. So it would be this way. In the exam, they can ask you about the overlaps. And what are the bonds that we have? We have 5 sigma bonds and 1 pi. Lastly, the last example, last type is sp hybridized. In the sp hybridization, we have one s and one p. Out of these, only this and this will react and make two hybridized orbitals. So we get two sp and sp orbitals. So one carbon has two sp or p orbitals. So carbon has just two bonds. So we take another carbon with two bonds. Ultimately, this will join with hydrogen. But carbon still needs to make three more bonds. Because this is an sp overlap. This is an s overlap. This is an s overlap. But remember, two p orbitals were still left unhybridized. So we make them here. So now they are going to be undergo overlaps. So how would the final structure look like? Not like this at all. We just make clouds. We get one cloud here. Let's change the color. Then we get another cloud. So that is what we get. Remember, two clouds is one pi bond. Like these two clouds make one bond, and these two clouds will make another bond. So how many bonds do we get? We have one carbon-carbon, one carbon-carbon, single bond with hydrogens, and two more bonds because there were two p clouds. So this is ethyl C2H2. Last thing about today, what are the overlaps here? So we have one sp overlap, two sps overlaps, and two pp overlaps. How many bonds? 3 sigma bonds and 2 pi bonds. So, and the angle would be 180-degree linear shape. So, whenever carbon is making 3 bonds, whenever carbon is making it this way, that's sp hybridized. Now, look at this one carbon. What is this one carbon making? One carbon is making 2 sigma and 2 pi's, right? 2 sigmas and 2 pi's. Let's take an example. Carbon dioxide. It is just making double bond. Here it was making triple bond. But it has a linear shape. It has 180. That's one hint. But we have just one carbon here, so let's see what the carbon is making. In every double bond, the first one is always sigma and the second one is always pi. So this carbon is making 2 sigma and 2 pi. And whenever carbon is making 2 sigmas and 2 pi's, that is sp hybridized. And students, that is all for today. Remember, sp3 is for single bonds, sp2 is for double, sp3 is for triple. But we also count the number of sigmas and pi's. So that's all for today. Thank you so much.